Good morning, everybody. I am Maocai Wang. My presentation type is trajectory optimal design for asteroid deployments based on mixed order. The presentation mainly introduces our method and design to attend the fourth contest of National Space Orbit Design in China. Okay. Today I talk from the following 5 parts. First, about the background. As we know, the asteroid exploration has become the research focus in the deep space. Some of research may be unlikely to predict and analyze the impact risk, and some maybe want to understand the long-term orbit and the active evolution, and so on. Global trajectory optimization competition, abbreviated GTOC, was launched by Advanced Concept Team (ESA) in 2005. GTOC is based on these missions being planned in deep space, and the purpose of GTOC is to stimulate the research in the area of the spacecraft trajectory design and optimization. Since 2005, GTOC has been organized 6 times. Now GTOC 7 is in progress, and we will disclose the competition problem in the end of this month. Since GTOC 1 in 2005, some universities in China have attended the competition. Tsinghua University is one of the typical and outstanding representatives. In GTOC 1, Tsinghua University ranked 11th. Here, Glasgow University also attended GTOC 1 and ranked at 7th. This table is the result of GTOC 1. Here is Tsinghua University, and here is Glasgow University. In GTOC 5, Tsinghua University ranked at 3rd, and the University of Spacecraft also attended GTOC 5, ranked at 11th. This table is the result of GTOC 5. Here is Tsinghua University, and here is the University of Spacecraft. Inspired by GTOC, in 2009, Tsinghua University and the Chinese Society of Theoretical and Applied Mechanics launched the contest of national orbit design in deep space in China. This is the Chinese version of GTOC. The contest was organized once a year. Like with GTOC, the contest is based on these missions being planned in deep space. Its purpose also to stimulate the research in trajectory design and optimization. In 2012, the contest changed its name as Contest of National Space Orbit Design in China, abbreviated as CNSOD. In 2012, CNSOD 4 was held in Beijing. Our team attended the contest for the first time. Now I will give our method and the result. First is the problem description. The problem definition of CNSOD 4 is similar to GTOC 2. In the problem, the spacecraft performs multi-task exploration by introduced with 4 groups of things. The purpose of the mission is to design and optimize the spacecraft trajectory to explore inner orbits, include asteroids and comets. The optimization objective is to maximize the overall mission return. In the mission, there are 4 group task objectives needed to explore. The first group is 1,750 years of asteroid. The second one is 2,065 million asteroid. And then 11 large asteroid and 653 comets. Here, the large asteroid means the diameter is more than 450 kilometers. In the problem, there are 4 mission types: we do with or without device, flyby, impact, and sample then return. And for every universe, the spacecraft can release or not release an exploration device. This is the means with or without device. This table gives income scoring systems. Different objects at every mission types have different income. Here, A, B, and C is the weighting coefficient. The value depends on the state type or the impact velocity or the flyby velocity. Here, these formulas give the specific method to compute the weighting coefficient A, B, and C. In the mission, there are 2 properties with the chemical property and the electric property, or their combination. The total exploration time is limited to 50 years. There are 2 main constraints. First, the minimum distance between the spacecraft with the Sun is not less than 0.2 AU. Second, the residual mass is not less than 500 kilograms when the exploration is ended. Now I give our method. The traditional idea is a 2-stage method. First, to determine the sequence of target asteroid, and then to optimize the launch time and the encounter time. The exploration sequence is a typical combinational optimization problem, where the trajectory design is a function optimization problem. The possible methods to solve the problem are branch and bound method or grid method. However, it will take too much time to search the global optimal solution with the branch and bound method. And for grid method, every step of the algorithm is based on the current optimum. This makes the solution not the global optimum. In our method, the problem was solved in one stage. That is to say, the exploration sequence and the encounter time can be optimized at the same time. We adopt iteration evolution by mixed coding. The main challenge is how to design the chromosome in a uniform way for the exploration sequence and the time sequence. Here, this picture gives the chromosome structure. The chromosome includes 4 parts: the exploration sequence, the mission type, the time sequence, and the breaking time. They are connected in order, but not in fixed length. The first part implements the exploration order of the small bodies. Because the coding for the whole chromosome is a solid state, the match between this part with the exploration sequence is implemented by random operation. The second part implements which one of 4 types in order to explore the small body. The match between this part and the mission type is implemented by judge whether the asteroid can be explored by this type. If it can be explored, the time sequence represents the launch windows and the encounter time. In the third part, the fourth state is the launch time, and the other state is the propulsion, that the time space accounts for in the whole information period. This method can ensure the total time doesn't exceed the given range. In the master form, replace the return time. Because the mission required the spacecraft must return to Earth after the operation is ended. So we set it to ensure the spacecraft can have enough time to return Earth after having completed the operation. Here is the algorithm process. The process is based on differential evaluation. The mutation, the crossover, and the selection were operated according to these formulas. Now I give our result. This table gives our method's result for the contest. This formula is the object is deployed and the mission type. Here F means flyby, IM means impact, R plus P means rendezvous with device. This column gives the total income and the rendezvous outcome. The object from the top to bottom means the exploration sequence. Here, this table gives the income for every object deployed. This date is the income for every object. And it also shows the result requires the main constraints. This picture is a simulation of the return trajectory. After the spacecraft returned to Earth from the last asteroid, the main-belt asteroid Propulsion. This is the return trajectory. There are 26 teams who resist in the contest. Only 13 teams' results were verified to be valid. Our results ranked at X in all teams, and among the regular universities ranked at second, only after the Tsinghua University. Here is the 13th team's result. And it is also partly present the most influential universities and research institutions in China's area space field. This picture is a screen of our team who attended the award ceremony in Beijing. This graduate is a representative of our team. The result shows our method is simple, effective, and especially suitable for the combinational mechanization of programs. That's all. Thank you.